Hey guys, for the first example problem in this course, we are told that we were working hard all week long. We got our homework done before the weekend began, and as a reward for our diligence, we get to relax and play some Xbox over the weekend. In this problem, we're told that while we're sitting in front of a flickering screen, there were 2.73 times 10 to the 24 electrons that passed through our Xbox. We're asked to find how many coulombs of charge went through our Xbox over the course of the weekend. Fundamentally, this problem is just a unit conversion. We are familiar with quantities like kilograms and meters and miles. We could convert some given distance from miles to meters fairly easily. We're used to problems like that. We're not really used to coulombs of charge and units of the elementary charge, but ultimately that's all this problem is. So we could go to the textbook and look up the charge of an electron. We'd find an electron has a charge of negative 1.6 times 10 to the negative 19 coulombs. Well, we could ask if one electron has that much charge, how much charge in coulombs does this number of electrons represent? Now, one electron is a really small particle. It will have a really small amount of charge. But this is a lot of electrons. This is about 0.5% of Avogadro's number, which itself is going to be huge. So we could set up a ratio. One electron equals this much charge. This many electrons equals that much charge. Or we could just say, if I have 2.73 times 10 to the 24 electrons, and I say the charge of one electron is negative 1.6 times 10 to the negative 19 coulombs per one electron. Then I could cross out those, and when I multiply these numbers together, I get negative 4.37 times 10 to the 5th coulombs of charge. And this is the amount of charge that went through my Xbox over the weekend. Now, if you are reading the textbook, you will probably come across something that says a coulomb of charge is a lot of charge. That is a true statement. However, remember, the electrons are flowing through metal, and from the electron C model that we discussed, if one electron moves to the right, there's going to be another electron that comes in to take its place. So the metal in the wires of my Xbox or whatever other device is plugged into the wall isn't really ever going to acquire a lot of charge. The charges are moving, so you get a lot of charge flowing through the machine, but the machine itself never really becomes charged. 100,000 coulombs is a really large number of coulombs on its own, but when it's all moving around and you have new charges replacing the old ones that left, ultimately the device remains relatively uncharged. For the first example problem involving Coulomb's force, we are going to investigate the force on an electron in a helium atom. We know that helium is the second element on the periodic table. The typical helium atom will contain 2 protons and 2 neutrons in the nucleus, and then there are 2 electrons in the electron cloud surrounding the helium atom. The picture we have here, the characteristic size of a helium atom is 31 picometers in radius, so that's 31 times 10 to the negative 12 meters. This picture is not really drawn to scale. A more accurate representation of an atom, you would see the nucleus being something the size of, we'll say, a grape at the center of a professional football stadium. And then the electrons in the electron cloud might be something like a microscopic grain of dust way up in the outermost seats in the 300 levels of the stadium. This picture is not exactly representative, but it's good enough for solving a problem. When we work with Coulomb's law, the style of thinking we will use is very similar to the style of thinking that we used when we worked with Newton's law of gravity last semester. Last semester, we learned that the gravitational force on an object from another massive object is given by Newton's gravitational constant, big G, times the mass of object 1 times the mass of object 2 divided by the distance between the 2 objects squared. Coulomb's law, describing the force on charged particles, is given as Coulomb's constant, times the electric charge of particle 1 times the electric charge of particle 2 divided by the distance between the two particles square. Look at how mathematically similar these two equations are. On the left-hand side of the equal sign, you have a force. On the right-hand side of the equal sign, the force gets weaker and weaker as your distance increases between the particles. Specifically, the force gets weaker as 1 over r squared for both gravity and Coulomb's law. In the gravitational force, we have the product of the two masses. In Coulomb's law, we have the product of the two electric charges. It is not incorrect when you are working with the force of gravity of thinking mass as being like the gravitational charge. And in both of these force laws, we have a fundamental constant of nature. Well, whenever you're solving a problem, you could always take something and multiply it by a constant. That isn't really too much work to do. Here we have Newton's constant of gravity that you will be given on an exam or you just look up in the textbook. Here we have Coulomb's constant, which again, you will be given on an exam or you just look up in the back of the textbook. So these two force laws look very similar, and a lot of the style of thinking when we actually solve problems with the Coulomb force will be similar to the style of thinking. The big difference for what we do in the beginning of this course is that Coulomb's force can be attractive or repulsive. The force will be attractive if the two charges have opposite sign. One is positive, the other is negative. The force from Coulomb's law will be repulsive if both charges are the same sign. Both charges are positive or both charges are negative. When we worked with the gravitational force, the force of gravity was always attractive. But that's not too bad to accommodate. We just throw on a direction at the end of a problem. So how am I going to think about determining the force on an electron due to the helium nucleus? We could say that the force is given by K. Coulomb's constant, that's a fundamental constant of nature. In a homework problem, we could go to the textbook and just look up the value. On an exam, you would be given that value. So the force is going to be K being 9 times 10 to the 9. Then we have the charges of our two particles. In this case, the nucleus of the helium atom is attracting the electron. The nucleus contains 2 protons. A proton has the same amount of charge as an electron, just opposite sign. Because we have 2 protons here, I could say the nucleus of the atom will have a charge of 2 times 1.6 times 10 to the negative 19. And then the electron has a charge of 1.6 times 10 to the negative 19. 1.6 times 10 to the negative 19. So this is the charge of 1 proton. Then I double it because we have 2 protons in the nucleus. This is the charge of 1 electron. I only have 1 electron that I'm looking at. We are ignoring the other electron in this problem. Then the distance between the nucleus and the electron in the electron cloud is 31 picometers. So that would be divided by 31 times 10 to the negative 12, and I square that number. Remember that you always convert to coulombs and kilograms and seconds and meters. It will be common on homework problems to see charges given in units of microcoulombs, nanocoulombs. When you're dealing with atoms, you'll often see units like angstrom, picometers, nanometers. Be aware that all these units need to be converted to the base SI quantities. At this point, I will just need to be careful about entering these numbers in a calculator. There are lots of parentheses. I need to remember to square because r squared. I need to be careful about raising to powers of 10 and positive exponents versus negative exponents. When I put these numbers in a calculator, I find that the force on the electron is 4.8 times 10 to the negative 7 newtons. So it sounds like this is a really weak force. This is the force that binds the electron to the helium atom. If this force were different, chemistry would be very different. The electron energy levels would be very different. Atoms would bond differently. Let's see what this looks like in the context of, we'll compare it to the strength of the gravitational force on the electron. Let's suppose this helium atom is somewhere near the surface of the Earth. So if I want to think about that question, we could say, how do we determine the force of gravity on an electron near the Earth's surface? There are two ways we could think about this problem. We could say the force of gravity on an electron near the surface of the Earth will be gravitational constant times the mass of the Earth times the mass of an electron divided by the radius of the Earth squared. We're assuming the electron is near the surface of the Earth, so the distance from the electron to the center of the Earth, because the Earth is approximately a sphere, is going to be the same as the radius of the Earth. But remember, back in Physics 121, we also demonstrated you could write the force of gravity as being equal to m times 9.8. And the reason for that is the product of Newton's gravitational constant times the mass of the Earth divided by the radius of the Earth squared is 9.8 meters per second squared. That's where that number comes from. So I'm just going to take the easier route with less math to worry about and say the force of gravity on the electron is going to be the mass of the electron times 9.8. The mass of the electron is a number I could look up in a textbook. I find 9.1 times 10 to the negative 31 kilograms. So I could say the force of gravity on an electron would be 9.1 times 10 to the negative 31 kilograms times 9.8. And when I put that number into a calculator, I find that the force of gravity on the electron is 8.9 times 10 to the negative 30 newtons. So let's compare these two numbers. Even though the strength of the force holding the electron to bound in the helium atom is small, 10 to the negative 7. Remember, electrons are fundamental particles. They are really small. This is still a factor of 10 to the 23 times larger than the force of gravity on the electron.